I think we can get started.
Okay.
Welcome, everyone. For those of you who don't know me, I'm Pedro Fernandez Caban. I'm an assistant professor here at the Seminar-FSU College of Engineering. My background is civil engineering, primarily wind hazard research. I would call it wind structural engineering. This is the first of a series of seminars that we're going to have this fall semester. For the grad students, the civil engineering graduate students, I sent some announcements and a tentative schedule for the semester, which might change depending on as far as times and the speakers, so it's tentative to change. But I just wanted to give everyone an idea of what the schedule is going to look like. So we can get started. So today I'm excited to have Dr. Omar Nofal from Florida International University, or FIU. He's an assistant professor there. How many years have you been there, Omar? Is this your second or?
Second year.
Time flies, I'm sure.
Yeah.
So he's going to be presenting today about high resolution community level flood risk and mitigation and analysis approaches. So the floor is yours.
All right. Thank you, Pedro. So hello, everyone. So again, my name is Omar Nofal. I'm an assistant professor at Florida International University. Today, I'm going to present part of my PhD work. So under the title of High Resolution Community Level Flood Risk and Mitigation Analysis Approach. So to start with, a brief introduction, as we know, like natural hazard risk is a combination of, is there something wrong? Can you hear me?
We can hear you, Omar. You're good.
Oh, okay. All right. So natural hazard risk in general, not only flood hazard, has three components, which is the hazard, exposure, and vulnerability. And in this research, we developed high resolution of these three components to capture high resolution risk analysis for the flood consequences. And this can be the methodology that has been applied here was applied for many communities. This includes communities that are exposed to riverine flooding, coastal flooding, so it can be applied for different types of flooding. So the methodology that we have developed is a high resolution enough that it starts at the component level and keep getting stages until it goes to the building level and the community level. So we used component level data such as the component type, the component elevation from the ground, the component replacement cost to account for losses. So we needed to have all the information within the building, within the high resolution information about the component within the building, this including, for example, furniture, appliances, electronics, so that we can account for building level damages. And also we use detailed building information such as the building value, building location, building archetype, occupancy, versa floor elevation, the foundation type. All these informations has been accounted for building damage. And when it comes to community level data, we use digital elevation map of the study area along with the land use and soil map to get a flood hazard map at the community level. So this mix of component, building, and community level allows us to do risk and damage analysis at the component level and stage this to the building level and then to the community level. So let's see how the component level data helped us. So the component level data allowed us to identify the failure probability of the components at different flood hazard intensity. So we developed fragility functions at the component level. For example, if you have flooding hitting a building, we know what is the failure probability of the TV or the AC unit or the dry walls. So we accounted, as you can see here, 100 fragility function for the different components within the building. However, to move this from the component level to building level, we developed, for example, damage states that can describe the different damage levels that can happen for a building. And we group these components based on their contribution to each damage state. And then we were able to capture the exceedance probability of each damage state for the building at different flood hazard. intensity based on the component performance during the flooding. Then to shift this approach from the building level to the community level, we developed what's called a portfolio of building archetypes, and then we developed vulnerability functions for these archetypes and assign them for the different building typologies within the community so that we can identify the damage for each building type within the community according to the flood hazard intensity that each building is exposed to. The way that this method has been developed in terms of staging and resolution from component to building and community level allows us to do mitigation analysis at these different resolutions. Like, for example, if we have some component level mitigation measures, such as using flood resilient materials or elevating water sensitive components from the ground. So since we have components fragility, it allows us to know what is the difference in the failure probability of the component if we are using flood resilient material or if we elevate the component elevation. Some people choose to put the EC unit, which is outside the housing unit, at a different elevation. So we can capture how this is going to impact the total building, how this going to capture the component failure probability, and how this is going to enhance the building performance. Same thing with building level mitigation measures. We were able to capture the impacts of using water pumps, buy out some buildings within the floodplain, using flood barriers to protect the building, or even increasing the building for various floor elevation. And definitely we were able to capture the community level mitigation measures and their impacts on each building. This includes building levees, dams, flood walls, floodgates, or even building retention systems. So this is an overview of the method, and I'm going to expand on each one of these boxes moving forward. So this is kind of most of the work that has been done in my dissertation when I was doing my PhD. We have done risk analysis, we have done resilience analysis, and also we were starting to do some recovery analysis. So for risk analysis, as I mentioned, it has three components: hazard, exposure, and vulnerability. And when we talk about hurricanes, the flooding is a part of the hurricane hazard components. So you can have also wind, flooding, and waves. And right now we are focusing on the flood components. Same thing, exposures. Building is not only the exposed assets within the community. We have lifelines, including transportation network, power network, water network. So in this seminar, we are focusing on buildings vulnerability. And for vulnerability analysis, we can use fragility functions, or we can use loss function. I'm going to present what is the difference between fragility and loss functions and how we develop them. Also for resilience analysis, we investigated many pre-disaster and post-disaster mitigation measures that can be done at the short term and long term, or even at the building level or the community level. So we have done lots of analyses to investigate many mitigation measures. For recovery analysis, we included our models with other social and economic models to account for the building's functionality. And this is going to come forward, like right now we have some publications under review that includes how we can integrate this work with some social and economic models to account for the total building functionality. Since building damage is only one thing that can contribute to the building functionality. However, there are other many components that can contribute to these functionalities, such as the functionality of utilities like water, power, or even the accessibility to different services. So all these contribute to the building functionality. So with this, let me start with an example that we have here, which is the flood risk analysis. So right now, I'm going to present my work that we have applied this methodology for many communities. I'm going to present only one community as an example for the application of the flood risk analysis approach that we have developed. This community is Lumberton, which is a small city within Robeson County, which is in southern North Carolina. So this is the geographical location in the city, and this is the boundary of the county with respect to the state of North Carolina. And this map shows how the city look like. The green dots here, or even all the dots here, are the buildings color coded based on their typologies or based on their occupancy. Most of the green buildings here are residential building. The red, yellow, orange building are either like commercial buildings or social institutions, including hospitals and schools. Let's first see what is the hazard modeling include for this community. So we developed the hazard model, a very high resolution hazard model for this community. So we use the digital elevation map of the study area, and we have done some like different analyses to perform hydrologic modeling using detailed rainfall information along with the land use and soil to identify the amount of water flow in each stream within the study area during an extreme event. So the hydrologic analysis only allowed us to capture a hydrograph. The hydrograph is like the amount of water flow over the time. So if we have an extreme event, so the water flow peaks up, and then after the event, it peaks down. So this is the main purpose of doing hydrologic analysis, is to capture how is the flow is it changing in the main rivers within the study area. Then we use this flow hydrograph as a boundary condition for a hydrodynamic analysis to develop a hazard map. And this flood hazard map basically capture the spatial distribution of the flood hazard intensity, like the spatial distribution of the flood depths across the community. Then we overlay this flood depths with the exposed assets like buildings and infrastructure to identify the level of exposure of each asset, like what is the flood depths at each building or at each infrastructure. Once we identify the flood depths or the flood velocity and the flood duration at each one of these assets, we can use vulnerability functions, which can be fragility or loss function. And that tells us what is the failure probability of this asset corresponding to the flood depths that this asset is exposed to. So this is basically an overview of the flood risk analysis approach. So let's see what flood scenario that we have here. So we use the rainfall event after Hurricane Matthew in 2016 as a hazard scenario for this study. So Hurricane Matthew started as a Cat 1 storm in September 29, 2016 in the Caribbean, and intensified as a Cat 5, but when it made landfall on the coastal line of North Carolina, it made landfall on October 8th as a Cat 1 storm, but it brought lots of rainfall and for the inland community. So it wasn't only a coastal crisis, but also inland communities such as Lumberton has been exposed to lots of rainfall. So the rainfall event from Hurricane Matthew resulted in 10 inches of precipitation. So as we can see here, this is a raster map of the precipitation across the US, or most of the areas that has been exposed to rainfall within the US. And as we can see, almost like North Carolina here, and the Lumberton city is around this location, which is the maximum amount of rainfall, which is 10 inches. However, most of the states has been exposed to lots of flooding, but not as intense as Lumberton. So this 10 inches of rain allowed Lumber River to rise to 24 feet height, which is higher than ever recorded, and the water kept to fill the river to swell and overflow the entire community of Lumberton. So we used these rainfall information to perform hydrologic analysis, and we identified the amount of water flow in the main streams that deliver the water to the study area. And as we can see, here's the geographical location of Lumberton, and the blue lines are representing the main rivers that deliver the water to Lumberton. So the mission from hydrologic analysis is to identify the water flow in the upstream, so that we can account for the amount of water flow in the downstream in Lumberton and identify the flood depths. So once we identified the water flow in terms of a hydrograph that capture the water flow over time, we use this as a boundary condition for a hydrodynamic analysis. And this is the result from the hydrodynamic analysis that we have done that shows how the water from the two streams get together to enter the city at some location. Like if we can see, most of the city is protected. Here's a levee that protect the city. But however, there's like a gap in one of the roads, like there was like an intersection between the railroad and the bridge here that allows the water to enter the city. So this was the main area that allows lots of water to get into the city. And this is a close-up view on the state of flooding at the same bridge from a different flooding. 2 years later, after this event from Hurricane Florence, it have the same issue, but this flooding was much less than the one that comes from Hurricane Matthew. We also have done other like other scenarios, like we have investigated like low return period event, like what if a 10-year return period event have happened in Lumberton. As we can see, the city is protected against 10-year event, just like a few amount of flooding, like a few inches of flooding in some areas. However, other than that, everything's good. Like the amount of the water is flowing in the streams that allows to be flow in. And we have simulated a 200-year event, which like kind of similar to the flood event after Hurricane Matthew. As we can see, same flooding behavior and around the same flood hazard intensity at most of the impacted Lumberton areas. So this is for hazard modeling. So right now I'm going to shift to the community and exposure modeling. So we know the state of the hazard intensity across the community, but we want to know what assets that are exposed to these flooding. But first, we need to identify these assets. So to identify the assets exposed to the buildings, we had there wasn't many information at that time about the buildings in Lumberton. So we use Google Stream Map View to navigate the Lumberton city building by building, collecting detailed information about the buildings, specifically the versa-floor elevation, because the versa-floor elevation is one of the main like parameters that accounts for the amount of flood damage inside the building. But we collected other information, including building material, number of story, occupancy, building use, building archetype, foundation type, ground elevation, building area, maintenance status of the building. We collected lots of information about these buildings. Then we developed a portfolio of 15 building archetype. These archetypes include residential building, like we have 4 residential building, F1, F2, F4, and F3. We have a bunch of commercial buildings, including gas station, a strip mall, super shopping centers. Also, we have some social institutions, including hospitals and schools and community centers. So we developed these archetypes to represent the different building typologies within the community. These are like the table that shows the description of each one of these archetypes. So we have 15 from F1 to F15. Some of them are residential, some are commercials. We have some office buildings as well, warehouses. So lots of building archetypes that can generally describe the different building occupancies within the community. Then the next step or the next challenge is how we can map these 15 building archetypes to the different building typologies within the community. So we developed a mapping algorithm that used detailed information about the building within the real community and assign the 15 building archetypes that we have to this community. For example, it makes like an if statement. So we are doing some check. If this building is residential, is it a 1-story or 2-story? What kind of foundation? And based on all of this, assign archetype 1. If it's like a commercial building, is it a gas station? Assign archetype 5. Is it like Walmart? Assign archetype 8, something like that. So this is what the mapping algorithm is doing. So this is an example of communities that we applied this mapping algorithm to. So on the left side is the real community, and on the right side is the mapped community. And the buildings are color coded based on their archetype. So if it's yellow, means residential, maybe it's 1-story or 2-story. So each different archetype is given a different color. After then that, once we identified the community and the assets and their types, we overlay the hazard model that we have with the community model that we developed to identify which building is exposed to flooding and what is the flood hazard intensity at each one of these buildings. What is the level of flood hazard intensity? Like what is the flood depth? What is the flood duration? What is the flood velocity? And we applied this to many communities. This is just one example that shows how is we accounted for the exposure at the community level. So the next step is to do vulnerability analysis. So we identified the hazard intensity at each building. So next we need to know if a building has a 2-meter flood depth, what these 2 meter can do to this specific building. And definitely if this building is residential, it's completely different if this building is commercial, because everyone has different components. So we developed a single variable and multivariate flood fragility and loss analysis approach for buildings. Basically, if we have a building, we divided this building into components, and we studied the flood susceptibility of each one of these components separately. So, for example, we used a probabilistic approach using a truncated normal distribution that use the upper and lower bound of the elevation or the damaging depths and the damaging duration for each component. For example, if you have a TV in your home, this TV can be mounted on the wall, like at a 1.5 meter from the ground, or it can be on a table, like 2 foot from the ground. So you have an upper bound and lower bound for the elevation of the components. Same thing, the AC unit. Some people can have the AC unit on the ground or can have the AC unit elevated from the ground. So we did this for every component, and we used the Monte Carlo simulation to propagate the uncertainties in the elevation and the damaging elevation and the damaging duration in each component. Once we identified the failure probabilities of the components, we used the damage states that we developed to identify the exceedance probability of each damage state for the building. So this is an example that shows how's the probability look like. This is an example like for an AC unit. So this actually an image from Lumberton community. We have done lots of field study there. So I took this picture by myself. This actually the AC unit after Hurricane Matthew. Before Hurricane Matthew, it was lower than the ground. So that explains how there's uncertainties in the elevation of the components. So it can be on the ground or it can be elevated. So we used like a best engineering judgment to identify the upper and lower bounds of these for each component within the building, and then we used a Monte Carlo simulation by using the probabilistic parameters for the elevation of these components to propagate the uncertainties in the damaging that can happen for each component within the building. This like an example of the damage states that we developed from damage state 0 to damage state 4. So damage state 0 is like insignificant damage, like the building can be surrounded by water but not damaged. Damage state 1 is like having 2 inches of water inside your home that can cause damage to the carpet, flooring. Damage state 2 is like having 2 feet of water inside your home that can cause severe damage to your appliances, content, furniture. But damage state 3 is extensive damage, where the damage like reaches like maybe like 4 to 6 foot of flooding and cause severe damage, but not complete structural damage. But for damage state 4, which is complete damage, we assume that the structure have complete damage, like even damage to the structural system itself. The way that we did the vulnerability analysis, we divide the building into many components. So for example, like we have we have a building that has like 100 components. So from around like 60 to 100 component. So as you can see, we have like crawl space insulation, garage cabinet, flooring insulation, refrigerator, stove, washer, dryer. So we have every component, including content, furniture, structural, non-structural components, all of them listed. And we have all the statistical parameters for these components, and we grouped them based on their damage state. So for example, you will find some groups are in damage state 0, some of them in damage state 1, 2, and 3, and 4. This is based on our damage state description. This is an example results for one of the buildings that we have. So this is a 2-story residential building on a crawl space foundation. And as we can see here, I tried to have some components outside and point them in the fragility function. So this curves is 100 fragility curve for 100 component within this building. As you can see, like you have lots of components here, but you will be surprised that at 1 meter, you have lots of fragility functions are coming together. This is because most of the building appliances and furniture are around like 0.5 to 1 meter elevation. So at 1 meter, we can consider them that all of them are 100% fail. Same thing in the second story, you will find that lots of components are showing at the second story at 4 meters. So you'll have many components from the second story showing here in the fragility curves. So we used these curves to come up with only 5 curves so that we can minimize our effort when we're dealing at the building level. So we transfer this 100 building fragility functions into 5 curves that can tell us what is the exceedance probability of a specific damage state for this building. For example, we like the first 4 component represent, for example, curve number 1. This is based on actually this Excel sheet. As you can see, component 1 to 6 contribute to damage state 0. Component 7 to 13 contribute to damage state 1. So basically, for the fragility of these 6 components make up only 1 curve, which is damage state 0. And from 7 to 13 make up 1 fragility curve, which is damage state 1. Same thing was applied for many other archetypes. This is another example for a 1-story residential building. And as we can see here, same thing. These are the fragility curves for the components within this building. And I also added some loss curves based on these components. Like basically, the loss curves of the components can be driven from the component fragilities by multiplying the failure probability of the component by the price of the component. So for example, if you have a fridge that is worth $1,000 and the failure probability is 50%, you multiply 50 by 1,000, so the loss is going to be $500. And if you have 100% probability, so the loss is going to be $1,000, something like that. So as soon as the flood depth is changing, the failure probability changing, and also the losses is going to change. Same thing we have done with the building fragility curves. So this is the building fragility curve for this archetype. We were able to drive the loss curves from these fragilities. So it shows, for example, what is the state of losses for this building at each flood depth. So the blue line in the middle, the black line in the middle is the mean flood loss. And the red shaded area is 1 standard deviation for this loss. And all these dots is the simulation that we have, because we use Monte Carlo simulations, and it gives us like 1,000 point, like at each flood depths, it gives you 1,000 value of the amount of flood losses. And we use them to get what is the mean value of the loss. So this is how it shows up. And we compare these losses with the with Haz's loss function, which is the red curve. And it shows like a great match. So basically, they are completely different approaches in terms of the use. So basically, Hazes considered that the building, whatever the flood depth it has, the maximum loss that it can has is like 78%. However, in our approach, we assume at a specific flood depth, we can consider that the building reached 100% loss. So our function is getting to the 100%. Also, one of the unique things about the function that we developed, it's a multivariate. So we were able to include the combine the impact of flood depths and flood duration. So this is, for example, a 3D surface that shows the state of flood losses at each flood depths and each flood surface. And we overlay the 2D flood loss on the surface as well, so that we can see how they are matching together. So this is also, we have done this for the fragility function as well. So we have 5 surfaces. Each surface tells you what is the exceedance probability of a specific damage state at a specific flood depth and a specific flood duration. For example, if a building is exposed to a flood depth 2 meter for 2 days, we can go at 2 meter and 48 hours and capture the amount of the exceedance probability of each damage state. And I have them separately. So this is damage state 0, 1, 2, 3, and 4. We have applied this approach for all the 15 building archetypes. As you can see here, this is the 2-story residential building. We have also multifamily, 1-story multifamily buildings, gas station, shopping center like Walmart. And as you can see here, we build a BIM model for each one of these archetypes, representing each component within. Like actually, in this Walmart example, you can see the fridges, the aisles, every section within Walmart. We take a real footprint of Walmart, even the lodging area and all the storage area in the back. So we have every component. We actually modeled every component in each shelf. So we have all the components within any shelf. Same thing with like strip malls, multi-unit family business, office building. Like this office building is the same. We're including every computer device within this office, every component within each one of these buildings. Similarly, schools, hospital, community center. So we have done this for all these archetype. And this is just to summary this that shows the fragility curves for each damage states for the 15 building archetypes. So here from archetype F1 to F15. And this is damage state 2 with all the archetype, damage state 3, and damage state 4. I'd like to mention that the methodology that we developed for the flood losses has been used by the White House, by the Office of Budget in the White House, to assess the impact of climate change on the federal facilities. So the approach has been widely in the industry and also by many federal institutions, including NEST and the White House. So right now we have seen how the hazard models developed, how the exposure models developed, and how the vulnerability models developed. And all of these is still separate. So how we can combine these three high resolution models to come up with a systematic approach that can tells us what is the state of damage for each building within the community if it was exposed to a specific flooding event. So we developed a community level vulnerability analysis that use detailed information about the hazard, the building characteristics, the fragility curves, and do building by building analysis, identifying the exceedance probability of each damage state. For example, it says for building 1, identify the flood depths, use the specific fragility associated with this building archetypes, and calculate the probability of exceeding each damage state, and then the probability of being in a specific damage state, and identify what is the maximum probable damage state that this building is going to have. So, for example, a building can have a maximum probable damage state is damage state 2. Then we assign damage state 2 for each one of these buildings, and then calculate the losses for each one of these buildings. Once we identify this for building number 1, we go and keep looping until we finish all the buildings. So this is the results for the buildings within Lumberton, color-coded based on their damage states from 0 to 3. We didn't have a damage state 4, so that's what we have so far. With this, I'm going to shift to the next topic, which is the mitigation analysis. So how we took advantage of the method that we have developed to do a mitigation analysis at the community level. So there have been many mitigation approaches for buildings exposed to flooding. Some of them are at the component level, some of them are at the building level, some of them at the community level. However, there haven't been many approaches that can account for the amount of saving that the building is going to have. If, for example, if you use sandbags to protect your building, or even if you take advantage of the extra time that you have to elevate the water sensitive components, including furniture, electronics, like your computer, your TV, or any expensive component within your building that can be elevated in like 1 or 6 hours. So we were able to do this using this high resolution approach. So basically, we developed a framework that used all the details that we have, including the flood hazard map, the building characteristics, and also information about the flood mitigation measures that we are using. Either the homeowner is using water pump to decrease the flood duration, or either the homeowner is using, for example, a flood barrier, like a bladder dam or a sandbag system, or whatever system that he has. And then we do a vulnerability analysis using fragility on the left side. So this is the process for it. And on the right side is the a vulnerability analysis using loss analysis. Like we need to know the amount of flood dollars that this homeowner is going to save by using this mitigation measure. So we either can have the vulnerability in terms of damage or in terms of losses. So let's start first with using temporary barriers. So homeowners can use temporary barriers to decrease the flood depth. So basically, what we have done in our approach, if the flood depth is less than the barrier height, so the amount of losses is 0. But if the flood depth is more than the barrier height, so we are hitting the back to the curve. Same thing with the flood fragility. So if the flood depth, for example, if you have a flood barrier of 1 meter, so you have no damage, but if it's more than 1 meter, so you will jump back to damage state 2 and 3 and 4. Also, we investigate the impact of using a water pump to decrease the flood duration. And we take advantage about the multi-variate vulnerability function that we have. So we have the flood surface, and basically, if you are using a water pump to decrease the flood duration to 24 hours, so we have a flood loss curve for 24 hours duration. We have one for 48, 6 days, 8 days, up to 10 days. Same thing with the fragility. So
go to the NASA.
Same thing with the fragility functions. So we have here the fragility function 1 day, 2 days, 6 days, and also up to 10 days. Also, we investigate the impact of elevating like water sensitive component. What if a homeowner was able to elevate like TVs, computers, or any water sensitive component was in his building? So we were able to capture the difference with building has non-elevated components and elevated components, and show some loss savings about maximum 10% of the building value, which can be like maybe 20 to 50K based on the home value. Also, we investigated a combination of mitigation measure. What if the homeowner were able to use a flood barrier like sandbags along with bumps? So we combine these together to come up with loss curves that can tell us what is the combination of these mitigation measures gonna do in terms of flood loss reduction. Also, we investigated community level mitigation analysis. What if the, for example, the community plan ahead and try to like build a levee system to protect the area, or building a retention system like a pond to regulate the amount of water flow in the river. So here it shows the location of the levee that we proposed for Lumberton, and also a retention system for Lumberton. I'm gonna show like this is one example of one of the mitigation scenarios at the community level, and we enhanced the levee system, and as we can see, it provides a full protection for the downstream here in Lumberton, and tamed Lumber River to flow in its own stream. So with this, let's summarize and conclude the amount of work that I presented here today. So I presented a component-based multivariate probabilistic flood vulnerability approach for buildings. It accounts for the impact of flood depths and flood duration on the amount of damage and losses for buildings. The developed vulnerability approach was applied to 15 building archetype, and it's general and can be extended to be applied for any building of interest. And we conclude that the flood depths alone may not be enough to accurately predict the amount of flood damage, and the inclusion of flood duration would give a better estimate of the flood damage. The fragility-based multi-hazard vulnerability analysis that we have done, or the one that we have developed here, and can provide a mechanism to propagate uncertainties in the damage and the loss estimates for buildings. And combining structural and content damage can provide better estimate of the final damage, because most of the functions out there rely on mostly structural damage, but content damage is as important as a structural damage. For recommendation for future research, and actually most of these future research we have been working on, even we like just submitted like 2 papers this week related to this work. So one of them is to include the population dislocation resulted from building damage and disruption to the lifelines, including water and power network. Also in accounting for the indirect economic losses that comes from building damage and how this impact the economy using computable general equilibrium economic models. Also calculating the post-hazard functionality using comprehensive models that can use the output from the building damage along with the disruption to the infrastructure to identify what is the functionality of the buildings within the floodplain and how this impacts the population dynamics. Building and community level recovery models also can be benefit from the models that we have developed for damage. We also have done some research on optimal mitigation strategies that building can adopt using multi-objective optimization. So this is also work that has been published before. These are the reference if anyone is interested in reading more about the work. Actually, I have 8 publications here that handle most of the stuff that I presented here today. And lastly, I would like to thank most of the funds that supported this research, including the one from the National Institutes of Standards and Technology, also the Homeland Security and the National Science Foundation, and also NOAA, and definitely Colorado State University. And thank you, and I'm happy to take questions.
Thank you, Omar. Very, very nice presentation. And for all the grad students that are in the call, that's essentially how you should envision presenting your proposal defense or your thesis defense. Very concise and very timely as well. I have a few questions, but I'm going to open up the floor for questions. If anyone has any questions, they can either unmute themselves. If you prefer to ask the question using the chat box, you can go ahead and do that now.
Hello. Do you have my voice?
Yeah, I can hear you.
Yeah, I'm Mariam Fakti, and thank you for your great presentation. I have two questions, if you can answer me. Actually, I think that you mentioned it, but maybe I must have missed it. So you had a flood depth modeling, I guess, right?
Yeah.
And which software did you use?
We used HECRAS. That's
okay, HECRAS.
Yeah. So that's
And
basic. Yeah. Go ahead.
Okay, so and did you use the stream gauge water level from USGS data?
Yeah, so there was a challenge here when we used the we could have not have done hydrologic analysis because USGS provide the water flow at one of the upstreams, but one upstream like here at Red Spring was missing, so there wasn't any USGS gauge. So we had to do hydrologic analysis to identify the water flow at this gauge. And then we validated them with the USGS gauges, and then we have done all the hydrologic analysis for the study area to do the hydrodynamic analysis for next step.
Okay, great. And one more question, it was, I guess, on a slide 17.
Okay.
It was, I guess you found some building information, and
This
yeah,
one?
that's it. Yeah, that's it. And I want to ask where actually did you find this information? Because I want some kind of like roof age information for different buildings, and I don't know how I can get them.
Oh, you were asking how did I get the information for these buildings?
Yeah, exactly.
Well, I built these buildings from scratch, building by building.
Ah.
So
okay, I see.
Well, okay. So, we tried as a team to identify because right now these are 15 buildings, and the level that they are modeling the community has a specific resolution. And if we want to go up with the resolution, we need to make this 15 100 or more, maybe 200. So as soon as you increase the building typologies that you will have more accurate model. But we cannot develop fragilities for all these building only me, like by myself, to develop all these. So we decided to come up with 15 building archetype, and this is enough to model the most of the buildings. So as you can see, we don't have like building more than 2 stories. So if we have a building that have 5 story, it cannot be modeled but most of the buildings within the community after full navigation are around 1 to 2 story. So if we have a bunch like 10 or 15 that are multi-story, even so we have 20,000 buildings. So if we have like 100 or 200 that are 2,000, it's fine. As soon as we are trying to capture most of the building within the community. And these also, most of the vulnerable buildings are the 1 to 2 story building rather than the 5 or the 10 story building. And then we come up with these combination of buildings, and we agreed that these buildings are enough resolution for now to model these community. Once we agreed on these community, we tried to get some layout or general layout for these community. And I tried to search to come up with layouts. Some of the layouts, like for the school and hospitals, were out there, so I built them based on the layout out there. But other than that, I tried to, like, as you can see, most of the buildings are like boxes. So I didn't like go crazy on the layout. So just like I tried to model a specific or general building archetype. And I built the main model for each one of these buildings so that we can have realistic component for each building. Like we don't want to assume a level of component. Like if a building is as a 2-bedroom, I shouldn't assume lots of components like that can fit in like a 5-bedroom home. Okay, so that's
I
the
see.
reason that we did BIM model.
Okay, thank you so much. I appreciate it.
Yeah.
Very good. Any other questions? I had a similar question related to the building archetypes, but you answered it perfectly. So I know a lot of students.
Right now we are
Yeah.
trying to study the impact of the resolution. Like what if we reduce these 4 residential buildings to 2? How this is gonna mess with the losses?
Yeah.
Maybe it will be the same. What if we reduces this 4 to 1? Like what if we combine these curves and get the average of them and make them only one curve? So we only have one curve for the residential building, one curve for the commercial, and see how's the resolution of the portfolio is representing the community, something like that.
Got it. Yeah, that makes sense. Because I know a lot of our grad students, they work with GIS mapping, but I think resolution is usually a problem if you want to go really find high resolution.
Yeah.
And then other type of information you mentioned, for example, first floor elevation, which is critical for flooding. You mentioned the Google Street Camera, relying on that.
Yeah.
What other sources can you use to sort of extract that information?
Okay, so for the state of North Carolina, actually, state of North Carolina is one of the best well-documented states in the entire US. They have a very well-organized database for all the buildings. Like if you check the North Carolina One map, you can download the 10 million building within the state of North Carolina. Which it has actually detailed information. It can tells you how many nails in each panel on each roof within each building in the community, like within the community. So they have detailed information, seismic, wind, flood, even the first floor elevation, and that's when we do analysis with North Carolina, it's really like a piece of cake. But if you go to other states, it's really difficult to find these information. So, for example, we have done hurricane much more advanced model than this one because we include the surge and wave and wind for Waveland, Mississippi, which is a 3,000 building community. So we had to do building navigation through Google Street Map View. Same thing. We have, but it was like if it's a 3,000 building, we can do them. Like we can hire grad students to navigate the building like in like a month or so. But if like a large community, we have encountered a problem for Galveston County in Texas. It has lots of buildings. So we had to make some assumptions. Like for example, we know the foundation type for each building and we know the ground elevation. So for example, if a building on a slab and grade foundation, so we assume that the building is like 2 foot from the ground elevation. If it's a crawl space, we assume it's 6 foot. If it's a bile foundation, we assume it's 10 foot. So this is kind of reasonable assumption. Also, I know that there is lots of researchers out there that are using machine learning to using the Google Street Map View along with to do image recognition, and they recognize where's the floor elevation at, and so there's lots of research going on in this area.
Right, very good. I only had one final question, and I'll leave it at that. So the damage states that you mentioned for flooding, I think they were mentioned in a qualitative matter. Are those from FEMA, or where do those? Where can we find those?
Yeah, so we developed these damage state as a part of the NEST-funded Center for Risk-Based Community Resilience Planning. Since there's no fragility function for flooding, so it's not a mature research like seismic. So seismic has lots of research in terms of fragility functions developed for buildings. We also started like 10 years ago to have some fragilities. There was like just a few researchers that started to work on the flood fragilities, and we are one of them that we started in like 5 or 6 years ago. So there wasn't much damage states, but once we developed these damage states, and this is general, most of the damage states are insignificant a slight, moderate, extensive, complete. This is a general damage state description for any building, whatever the hazard is. But the thing is, we need to agree on the components that that can tell this building is a slight or moderate or extensive. So it was like expert judgment, and also matches what is the FEMA description for a damage state. So if you check the FEMA damage state for flood, it's almost the same. But what we have done, we got these damage ratios. Like we said, the insignificant is from 0 to 3%, 3% to 15% is slight. We have done detailed damage analysis for each building, and we know what the component that contribute to the slight, and we know the value of these components, and we got average of the 15, and it gives us this range.
Okay.
Yeah.
Yeah, no, that's excellent.
Right.
Any other questions? Very good. All right. I want to thank the speaker again. Thank you very much. Very, very interesting presentation. And I know a lot of our grad students and myself, we're going to take a lot out of it. Given that, I mean, we're working in very similar research here. And most of our research focuses on the Panhandle, Big Bend region for sure, but within the state of Florida as well.
Yeah, I have done
so,
like some research for Mexico Beach after Hurricane Michael. I'm not sure if you have done research in that, Bart. So we also use.
So perfect. So
yeah.
So if any of the grad students on the call would be interested, they can go to Omar's papers and look into that for sure. Perfect. Sounds good. So yeah, we'll leave it at that. Our next seminar is going to be next Friday. And then for the grad students, I'll keep you posted. As I mentioned earlier, you have a tentative schedule, but it's subject to change. So definitely keep an eye on your emails. I think there's I think we're good. Perfect. Sounds good.
All right. It was nice to present today to you.
Have a good weekend, everyone.
Yeah. Bye.